So we're looking at cylinders and quadric surfaces, and these are typical types of surfaces that we deal with in R3. So what we have here is a table that can help us kind of sort out the various types of quadric surfaces. And there's 6 basic ones that we'll be focusing on. The first one is, as we can see here, is an ellipsoid. Okay, looks kind of maybe like an egg or a football type shape. Generally speaking, its equation looks like this, where those denominators could be basically any constant. The only variables in this would be the x, y, and z. Now notice the note here that if those constants in the denominators happen to be identical, then the ellipsoid will end up being a sphere. The second type of surface is the elliptic paraboloid, and this is a commonly seen surface in Calc 3. The example we have here is of the form z equals something involving x squared and y squared. Notice that those denominators could be a variety of different constants. What's important to know here is horizontal traces are going to end up being ellipses. The vertical traces are going to be parabolas. And the variable raised to the first power indicates the axis about which the paraboloid is centered. Next we have the hyperbolic paraboloid. Now the hyperbolic paraboloid looks essentially like a saddle. The form of the equation is z equals something involving x squared minus y squared, and of course we can have constants here in our denominator. What's interesting here is that the horizontal traces are hyperbolas and the vertical traces are parabolas. Now, and they are indicating here that in this illustration we have the case where the denominator of the z variable happens to be negative. The next type of surface is a cone. This is its type of equation. The horizontal traces of a cone are ellipses. The vertical traces in the planes are hyperbolas, and so forth. Notice that it is of the form z squared equals x squared plus y squared, of course with various constant denominators. Okay, now our hyperboloid of one sheet is the next type. Notice that this is of the form x squared plus y squared minus something involving z squared equals 1. This type of equation creates a hyperboloid of one sheet. Horizontal traces are ellipses, vertical traces are hyperbolas, and the axis of symmetry corresponds to the variable whose coefficient is negative. So in this example, the axis of symmetry is the z-axis, and notice that the z term is negative. Lastly, we have the hyperboloid of two sheets. X squared, something involving x squared minus y squared plus z squared equals 1. So the horizontal traces are given here. Vertical traces are hyperbolas, and the two minus signs indicate that we do have two sheets. Notice there's a negative here and there's a negative here. So that's the clue to us that we have a hyperboloid of two sheets. Now, moving forward, the shapes that we will be typically trying to draw out of this collection will typically be the ellipsoid, the elliptic paraboloid, and the hyperbolic paraboloid, and possibly the cone. Rarely will we ever be attempting to draw these last two. In class, we'll talk about how to go about sketching them, but for now what we want to do is focus on categorizing them. So let's take a look at this first equation. This is going to be an ellipsoid. And how do I know this? I know this because I have an x squared term plus a y squared term plus a z squared term equals 4. Now, if I look at that formula there, we notice that that right-hand side should be a 0. And that's easy enough to fix by dividing both sides of this, I'm sorry, that was 1, dividing both sides of this equation by 4. In which case I would end up with something like x squared over 16 plus y squared over 4 plus z squared over 4 equals 1. And now that is in the form identified on that sheet. And the graph of this ellipsoid looks like this. Okay? Now we move on and take a look at a hyperboloid of one sheet. Looking at this equation here, how am I recognizing that I have a hyperboloid of one sheet? I have x squared term, y squared term, z squared term, only one of those of which is negative, and also my right-hand side is 1, which matches what we have here on our table. And so the graph of this surface would look like this. Moving on to recognizing a hyperboloid of two sheets. Again, I have a z squared term, a y squared term, and x squared term all on the same side of the equation. Two of those terms happen to be negative, and my right-hand side is equal to 1. That satisfies the criteria or the form of a hyperboloid of two sheets. And so it would look like this. Moving on to our next shape, our surface, the hyperbolic paraboloid. We can recognize this equation as being a hyperbolic paraboloid because we have one of our variables, in this case the z variable, is of degree 1. And on the other side of the equation, I've got an x squared term and a y squared term, one of which is negative and the other is positive. These are the clues to the presence of a hyperbolic paraboloid. And so the graph of this surface would look like this. Moving on to our next surface, the elliptic cone. I can recognize this as an elliptic cone because I have one of my variables squared equal to the sum of the squares of my other two variables. So notice in this case I have z squared equals a sum involving x squared and y squared. And because this is z squared equals, I know that the axis, the center axis will be the z-axis. And so I can go ahead and graph that, and it would look like this. The next surface we want to focus on is the elliptic paraboloid. The elliptic paraboloid equation looks like z equals the sum of x squared and y squared. Could even be z equals the opposite of those would be permissible as well. the difference between these two, this paraboloid opens up, and this paraboloid would open down. And we think of those in a similar way as parabolas. And so the graph of the paraboloid that we were given, we recognize as opening up, and that would be the graph of what that would look like.